Good day, ladies and gentlemen. In this first chapter, we are going to look at the introduction to quantum chemistry and quantum theory, and also some principles that we're going to use in the next chapters. So we're going to define some tools that are very important since we're going to use them later on. Firstly, I want to define the idea of different types of motion, since we are going to divide the quantum mechanical models that we're going to use according to the type of motion. Now, the first type of motion is translational motion. Now, translation is just something moving in a straight line. For example, a car driving on a road without changing lanes. Then we have rotational motion, and you all know what that means, something that rotates. And we also have vibrational motion, which we can imagine something vibrating on a spring forwards and backwards. So these are the three types of motions that we are going to look at. Okay, so now I'm going to move to the notes on Atkins, the chapter Introduction and Principles to Quantum Theory. This is chapter 8 in the 8th edition of Atkins, and chapter 7 if you have the 9th or the 10th edition of Atkins. So firstly, we're going to look at some background. Well, there's something called classical mechanics. So I'm going to take you back in history, and we're going to go back to the end of the 19th century. So at that stage, the scientists had Newton's laws, and we call Newton's laws classical mechanics. And these laws were very useful to describe the motion of macroscopic objects. Macroscopic meaning large. So objects in everyday life. We have equations for velocity, which is the rate of change of position with time. We can get average velocity. We have an equation for linear momentum, which we're going to indicate with the symbol P. Is mass m times velocity v. So using classical mechanics, we know the exact position of an object. For example, if you throw a ball in the air, you can calculate at a specific time the exact position of the ball. So at the end of that time, however, it was realized that these equations, Newton's laws, classical mechanics equations, were actually not very useful when it comes to very small particles. For example, electrons, photons, neutrons, etc. And it was realized that new laws were required. And these new laws are what we're going to look at in this course, namely quantum physics and quantum chemistry. We're going to have more of a chemistry approach in this course. And the reason why we cover this topic in chemistry is because we are working with electrons, with light, with protons, etc., with small molecules in chemistry. So we need to have the right type of laws when we are working with these particles. So this new mechanics was called quantum mechanics. So on the one side we had Newtonian mechanics, which are called classical mechanics, and then we also have the new laws called quantum mechanics. So we will often compare the two approaches to each other in this course. So in classical mechanics, we can know the exact position and the momentum of an object. And we'll often talk about a particle. Now, a particle can be anything: a neutron, a proton, your car, a ball, etc. So for a particle, this can be determined exactly in classical mechanics. Also, in classical mechanics, the different types of energies, be it translational, vibrational, or rotational energies, can adopt any value in classical mechanics, simply by changing the forces that apply to the specific objects. The classical view of light is that it is a oscillating electric and magnetic disturbance. If you think back to physics, it's electromagnetic radiation, and it spreads through space as a wave. So classically, we see light as a wave. Some more information about light. The speed of light, 3 × 10⁸ meters per second. In your data sheet, you'll find a more exact value that you can use in calculations. Wavelength of light, we will use the symbol lambda. Frequency, we will use the Greek symbol nu. It almost looks like a V. And for wave number, we use the symbol nu with a bar on top, which we are going to call nu bar. There's a relationship between wave number, frequency, and the speed of light, wave number, and wavelength. And this you will all find in your data sheet. And note that the wave number has a unit of per centimeter. You will also notice in textbooks that you sometimes find this symbol for wave number instead of nu bar, and this is called nu tilde. So that squeaky line is called a tilde. You also find this relationship in your data sheet. When you multiply wavelength with frequency, it is a constant, and this constant is the speed of light. So the first thing that we're going to look at is the experiments that made scientists realize that classical mechanics does not always work. So they made some experimental observations that they could not explain using Newton's laws. So we're going to look at the experimental evidence that showed that the laws of classical mechanics specifically cannot be applied to small particles. And these experiments are called the failures of classical physics. Now, the first experimental observation that could not be explained by classical physics was the observation of black body radiation. When you heat an object, it starts to emit radiation at high temperatures. Now, this is very easily described by taking a piece of metal and putting that metal in a fire, so heating it. Initially at room temperature, that metal is black. When you start heating it, it starts to glow, firstly red, and then if you make it warm enough, it starts to glow white hot. So that is the radiation that we talk about, the radiation that is emitted. And the higher the temperature, the shorter the wavelength emitted, so the more blue the light emitted. So that's why it goes from red hot to white hot. So if you plot the emitted wavelengths as a function of energy, this is the experimental graph that you will get. So this is experimental. So there we have wavelength, and there we have, just see that as energy intensity. And each of these different lines represent a specific temperature. And the temperature increases in that direction. So the higher the temperature, the higher the maximum point of this graph. So that will be a lower temperature graph, this will be a higher temperature graph. You'll also notice that as the temperature increases, the maximum of this peak moves towards the left, so to lower wavelengths. Just something in terms of energy. If you look at your data sheet, you'll see that energy is H, which is Planck's constant, times mu, which is the frequency. You can also write that as Hc divided by lambda. So energy is proportional to 1 over wavelength. So it means the shorter the wavelength, the higher the energy in this graph. So the energy peak will be higher. So if we plot energy here, shorter wavelength will mean higher energy radiation. Okay, so this is what they saw experimentally. Now they try to come up with a theory to replicate this, to explain this experimentally. Remember, that is what we do in chemistry. We see something and we then propose a theory to describe or explain what we see experimentally. Okay, so firstly we can explain this type of emission as black body emission, now, or black body radiation. Now, black body is something that we call an ideal emitter. The only thing you need to know about this is that it absorbs and emits all frequencies or wavelengths uniformly. It means that it doesn't retain any wavelength, or it doesn't absorb any wavelength. So for example, if you have an empty container that basically allows light to come in and the same wavelengths of light are allowed to exit. So nothing is retained inside the container. Okay, so they tried to explain these experimental observations firstly using what they had, which was classical mechanics. So the first person who entered the picture was someone called Rayleigh. He used classical mechanics because that's what he had, and he said that this graph was as a result of oscillators. So you can imagine in your metal rod you have metal atoms. These atoms vibrate because of the heat, they oscillate, and they oscillate at a specific frequency, and that is why you see a specific frequency, which is that frequency there, which is related to energy, which is related to wavelength. So you can also plot frequency on this axis. So that is why you see a specific frequency, because of the oscillator, your metal atom oscillating at a specific wavelength. And Rayleigh said, okay, according to quantum mechanics, these oscillators, these atoms in the metal oscillate at all possible frequencies. So any frequency is allowed. When he made that assumption, the theory predicted his graph to look like that. So here we have the experimental graph. There we have the theory graph according to Rayleigh, and you should definitely agree with me that that is not a very good fit. It works okay at higher wavelengths, but at shorter wavelengths it is very poor, because it doesn't show this maximum and it doesn't go to zero at very short wavelengths. To the contrary, it actually goes to infinity at zero, because this peak just increases, and that is a big problem. you guys don't have to know these specific equations. We're not going to look at that in that detail. All that you need to know is that it works well at high wavelengths, but it fails very badly at short wavelengths because it just increases, the maximum is not reproduced. And this is known as the ultraviolet catastrophe, because at these short wavelengths, which fall in the ultraviolet region, the intensity just increases, which is not at all possible, because this means if we apply classical physics to blackbody radiation, that even at room temperature, everything should be emitting light. It should glow. So that chair that you're sitting on, you yourself should be glowing. And we know that is not true. So classical physics does not work in explaining blackbody radiation. Okay, so they had to come up with a solution, and this is where Planck entered the picture. And he made a change to Rayleigh's assumption. He also used the idea of oscillators, metal atoms oscillating, and a frequency being observed as a result of an oscillator being present. But he said the oscillator is limited to discrete energy values. And this was the introduction of the idea of quantization of energy. Specifically, if the energies of the oscillators took on the values n times h times nu, where nu is the frequency, with n equal to 0, 1, 2, then you could reproduce this experimental curve that we saw in the beginning. Now, this symbol h in this equation is known as Planck's constant. Again, you don't have to know the specific equation, but in this case, if he only allows the energies to be equal to those specific values and not any energy, like Rayleigh assumed, the story looks much better, and this is the shape that his equation then predicts. So it solves this problem that we had at short wavelengths. And at long wavelengths, it actually gives the same equation as the Rayleigh equation. So by introducing the idea of quantization, only certain allowed energies and this quantum number, so n is known as a quantum number, it limits the energies to certain values. It solves the problem of blackbody radiation. And effectively what it does is these high energy oscillators, remember we said energy, because this is wavelength, so these are the high energy oscillators, need so much energy to be excited that even at very high temperatures they're not excited. That's why it goes back to 0. So the role of quantization then basically reduces the contribution from these high frequency or high energy oscillators. So they're not significantly excited at all, even if the temperature is fairly high. So again, to summarize, by introducing the idea of quantization, Planck managed to explain the experimental observation of the blackbody radiation curve that Rayleigh couldn't explain by just applying classical mechanics. Okay, then later on, there was a second experiment, or second experimental observation, that they tried to explain with classical mechanics, and that has to do with heat capacities. If you think back to your second year physical chemistry, you will remember that there were two people, De Long and Petit, and they looked at the heat capacity of compounds, and specifically they looked at monoatomic solids. So these are solids containing one specific atom. So it's not a molecule, it's an atomic solid. And they found that these values of the heat capacity of these solids are all around 25 joules per Kelvin per mole. How did they get to this? Using classical mechanics. Well, they used what is known as the equipartition theorem. And this is something you should remember from second year. So just in summary, the mean energy of each oscillating atom in this monoatomic solid is equal to kT in 3 dimensions. So this is for each direction, but we live in a 3-dimensional world, so you multiply that by 3. So it's 3 kT. If you have n atoms in your system, the mean energy becomes 3 nkt. If you work with a mole of atoms, your number of atoms becomes Na, which is Avogadro's constant, and then you also have a relation that says NaK equals R, so that becomes R. So the molar energy is 3 RT. To get heat capacity from molar energy, if you remember back to second year, it is the first derivative of the molar energy to temperature gives you heat capacity. So that would be 3 RT dt, which is just equal to 3R, because dt becomes 1. And then we have a value for R, we can multiply that by 3, and you can get the value, which is close to about 25, which is where De Long and Petit got their value from. Okay, so this is all good and well when you are working close to room temperature. So classic mechanics works well close to room temperature. However, when the temperature is reduced, so when they were able to go to much lower temperatures, and specifically when temperature goes to 0 Kelvin, they found that this is no longer true. So the heat capacities were no longer approaching 25 joules per Kelvin per mole. Okay, so now they tried to solve this problem, because then obviously classical physics, classical mechanics didn't work. In actual fact, if you plot heat capacity as a function of temperature, there's your value of 25 joules per Kelvin per mole. At high temperatures, that works fine, but you'll actually see if you plot this towards 0 Kelvin, these values drop. So they could explain that part, but they couldn't explain this part using classical mechanics. Okay, then Einstein, very famous person, tried to solve this problem. Again, introduced the ideas of oscillators, contributing to heat capacity, and he assumed that each atom in your monoatomic solid that contributed to heat capacity oscillated with a single frequency, and that frequency is nu. And he also used the idea of Planck, that the energy of these oscillators are quantized. He came up with a formula for heat capacity. Again, you don't have to know this formula. And ladies and gentlemen, you don't have to know the details. What you need to know is that if you use the idea of Einstein that a single atom, or each atom, oscillates with a single frequency, there is the experimental data of heat capacity, versus temperature, and that solid line shows you the fit of the Einstein formula. So it works fairly well, but you won't believe this, but actually Einstein made the wrong assumption by assuming that all oscillators have the same frequency. They actually oscillate over a range of frequencies. So all the atoms in the monatomic solid might not have the same frequency. So if that assumption is made, you get a much better fit, and that assumption was made by Debye, which shows, or which gives that solid line which lies exactly on the experimental data points. So the moral of this story is again that quantization has to be introduced to explain the thermal properties, in this case the heat capacity of the solids. So just to summarize that, firstly, Einstein assumed that all the oscillators vibrate with the same frequency. It gave a better fit, but a better fit than de Long and Petit, who all assumed they had the same value, but that wasn't true at lower temperatures. And then Debye showed that they actually vibrate over a range of frequencies. And then that fits the experimental data very well. We also have proof of quantization of energy from spectroscopy. Remember, spectroscopy is where we use electromagnetic radiation to analyze chemical samples, and the radiation can either be absorbed, emitted, or scattered. And we normally plot intensity of light that is absorbed or scattered or emitted as a function of frequency or wave number or wavelength, and then you plot your spectrum. So why do we say that this gives proof of quantization of energy? Well, you know that this is what a spectrum typically looks like. We have an example of an atomic spectrum and a molecular spectrum. And you see that you have discrete individual lines in these spectra. For a molecular spectrum, it's a bit more complex because you have a background, but on top of the background, you also have individual lines. Well, you can imagine if energy wasn't quantized, so if you have a continuous range of energy levels, then any transition would be possible and your spectrum would just be constant, because there would be that transition, the next one, the next one, the next one, the next one, the next one. However, because energy levels are quantized, so we have that level, but nothing in between, and that one and nothing in between. For example, if you measure the absorption spectrum, let's say frequency, from that level to that level, let's make that E0, E1, E2. For that transition, you see a line. For that transition, you see a line. But there's nothing in between, because there's nothing in between. So the fact that we see discrete lines in the spectrum, we know from that fact that energy levels are quantized. Otherwise, our spectrum would look like that. So this means that the energy of the atoms and the molecules there that we are working with are also discrete. Remember the energy difference between two energy levels, E1, E0, E1 minus E0, which is equal to H nu. Just something in terms of the relationships between the equations. This is an emission example. So if you have three energy levels, E1, E2, E3, and you have a transition from E2 to E1, E3 to E1, and E3 to E2, the wavelength of the radiation emitted from E3 to E1 will be very short, but from E3 to E2 will be very long. Now why is that? That is because wavelength is inversely proportional to energy. So that is a huge energy difference from E3 to E1. So energy is inversely proportional to wavelength. So if the energy is big, the wavelength is small. And vice versa, energy is small, so wavelength is large. So remember delta E is h nu. Mu is c over lambda. This is all in your data sheet. So energy is directly proportional to frequency. Frequency is directly proportional to 1 over lambda. So that means energy is directly proportional or indirectly proportional to wavelength. So if you have a large delta E, you have a small wavelength, small delta E, large wavelength. Okay, so we now know that energy is quantized for radiation and also for atoms. We're going to look at some additional experiments in a moment. But when we talk about the quantization of radiation, we already saw the equation E is h nu, or we can also write it as nh nu, with n being the quantum number, 1, 2, 3, so it's 0. Well, it can also be 0 if there's no light, or no radiation, 1, 2, 3, etc. And this can be seen as light consisting of particles. I haven't given you experimental evidence for, but I'll do so in a moment. And a particle of light is called a photon, and each photon has energy h nu. So I want you to think about the characteristics of photons. So here is some homework. For example, do they have mass? So if you are working in the garden outside in the sunshine, do you actually feel the photons hitting you? So think about that question. We've also talked about the spectra and the transitions. We're not going to look at this example where we calculate number of photons. You can look at that if you are interested. Okay, so I've just told you that light consists of particles with the energy h nu, but do we actually have experimental evidence for this, or do you just take my word? Well, the answer is we do actually have experimental evidence that particles, or that light consists of particles. And that experiment is called the photoelectric effect experiment. So what you do in this experiment is the following. You take a piece of metal and you irradiate it with UV light. Now remember, the classical view of light is that it is a wave. If you do that, you will find that electrons are ejected from the metal. And remember, the classical view of an electron is that it is a particle. These electrons have kinetic energy equal to half MeV squared, where Me is the mass of the electron and V is the velocity of the electron. Okay, so in doing this experiment, certain observations can be made, and these are listed in your notes. The first observation is that no electrons are ejected regardless of the intensity of radiation, unless the frequency of the light exceeds a specific minimum value which is characteristic of the metal. So this light coming in has a specific frequency nu. So remember, on this side we have the wave, on that side we have the particle, so don't get confused about the two. And they talk about the intensity of the light. So the intensity means how strong this light is. Is it a weak beam or a strong beam? That doesn't have anything to do with the frequency. So weak beam would be like 1 or 2 photons a minute. Strong beam would be like 100 photons a minute. Okay, so the first observation, no matter how strong or how weak, or sorry, in this case, no matter how strong the light or how intense the light, if that frequency is not high enough, no electrons are emitted. So that process does not happen if the frequency is too low. And that specific frequency is determined by the metal. Secondly, assuming the frequency is high enough, the kinetic energy of the electron increases as the frequency increases. But again, it's independent of the intensity of the light. Third observation, if the frequency is high enough, so above the minimum value, electrons are ejected even if the intensity is low. So if you have a very low intensity, 1 electron a minute might be ejected. If you have a high intensity, 100 electrons a minute might be ejected, provided this frequency is high enough. Okay, so how do we interpret these observations? Well, firstly, this experiment suggests that an electron is ejected when a particle with enough energy collides with the metal. So instead of seeing this light coming in as a wave, we now see this as a particle coming in, colliding with the metal, with the atom of the metal, and then kicking out an electron. So that's where the idea of light being a particle comes in. Because a wave cannot kick out an electron, only a particle can do that through a collision. So that's the first idea, or the first conclusion that we can draw from this experiment, that light is a particle. And then how do we explain these other observations? Well, firstly, it helps to write the following equation. Firstly, we assume that this particle of light is a photon, like we said before, with energy h nu. And then the kinetic energy of the of the electron is the total energy of the photon minus the energy that is used to remove the electron. So remember, this is the electron, that is the photon, and that is the work done to remove the electron from the metal. So some of the photon's energy is used to remove the electron, and the rest is transferred to the electron itself in terms of its kinetic energy. Now this funny symbol is known as the work function of the metal, and it's typical for each specific metal, and this is the energy required to move or to remove an electron from the metal. This is similar to what we call ionization energy, which is defined as removing an electron from an atom, from removing it to infinity. So work function is specifically for a metal. Ionization energy is much more general. Okay, so we can also then draw a figure in terms of energy. So let's say this is the work function of the metal. That is the minimum energy required, that's energy, to remove an electron. Now our first observation was, unless the frequency exceeds a minimum value, frequency is proportional to energy, remember energy proportional to frequency, unless you have a minimum frequency, no electrons are ejected regardless of intensity. So let's say your photon has this energy, E equals h nu. So clearly that photon does not have enough energy to overcome the work function. So in this case, no electrons will be ejected. That is your first observation. If your photon has that amount of energy, so that is h nu, some of that is used to cover the work function, and the rest of it, the remainder, will be kinetic energy. So there's the work function, there's kinetic energy. And this brings us back to that equation. The kinetic energy is h nu minus the work function. The kinetic energy increases linearly with frequency, but is independent of the intensity. That's our second observation. Kinetic energy increases with frequency, because remember that is a constant. So if that increases, that will increase, that remains constant. That explains the second observation. And then thirdly, if the frequency is above the minimum value, electrons are ejected even if the radiation intensity is low. So as long as your photon's energy exceeds the work function, electrons will be ejected, regardless of the intensity of the radiation. So this explains the observations for the photoelectric effect. So for this experiment, you need to be able to explain the experiment itself and also give the interpretation of these observations. And remember, this experiment specifically shows that light has particle characteristics. So light consists of particles. Okay, so now we have confirmed that light consists of particles or photons. Now we can ask a more controversial question, and that is, do particles consist of waves? So is that chair that you're sitting on actually a wave? And there are actually experimental evidence that confirmed this. So this was confirmed by an experiment that showed that electrons are diffracted. Now diffraction is typically a phenomenon that is observed by waves, classically. But now we see in this experiment that electrons are diffracted. Now remember, electrons we classically see as particles. So here this particle behaves as if it is a wave. So is matter wave-like? Does a particle behave like a wave? And the answer is yes. So in this experiment, we have a nickel crystal which acts as a diffraction grid. Electron beam comes in, so this is a particle, and it diffracts like a wave would normally be diffracted. So normally diffraction is the interference caused by an object in the path of waves. But now particles are diffracted as if they are waves, and you get this constructive and destructive interference, which is diffraction. So this shows us that particles actually behave as waves. And electrons are not the only particles that do this. Experiments have been conducted, well, on electrons, we've seen this, neutrons, and also even molecular hydrogen. So even atoms have been shown to diffract. So even atoms behave as waves. So this experiment tells us that particles behave as waves. So don't confuse this with the photoelectric experiment, which shows us that waves behave as particles. So you must be able to distinguish between the two. And if I ask you a question, you must know which experiment to give in the paper or in the question paper. Okay, so when considered at the atomic level, particles are waves and waves are particles. And this is known as the wave-particle duality. And there's actually an equation that combines these concepts. And that is known as the de Broglie equation, and we're going to use this equation a lot. Now the de Broglie equation allows you to calculate the wavelength not of a wave but of a particle. So you can now calculate the wavelength of the chair that you're sitting in, or you can calculate your own wavelength. The caveat, however, is that the wavelength or the particle that you are calculating the wavelength of must be moving. So in this equation, P is the linear momentum. So P is m times v, and h is Planck's constant. So the wavelength of a particle is Planck's constant divided by the linear momentum. Now guys, just think about this. We have another equation for wavelength, and here you have to distinguish between the classical and the classical views of these things. If you want to calculate the wavelength of a particle, this is what we would consider classically being a particle. So the wavelength of an electron, the wavelength of a neutron, the wavelength of a hydrogen atom, the wavelength of a silicon atom. So these things that are classically seen as particles, you would use the de Broglie equation for. If I ask you to calculate the wavelength of light, you would use the equation that you would find in your data sheet, which is that one. So that one. So don't confuse the two. This you only use for what we consider classically as particles. This you would still use for light. Okay, so in this lecture we looked at why scientists realized that Newton's laws don't work anymore, why they had to introduce the concept of quantization, and then we also looked at some experiments that showed us that waves are particles and particles are waves.